still have codecs. I mean, UAT actually changed the access rights. I think you don't have it anymore. Sweet. No, tell me. I mean, I lost access, but I lost access a day before because I ran out of credit, and it was like 2 days before. And then people told me, man, like actually there is no access whatsoever. So what's the state right now?
You can use the chat application.
Yeah, but CLI, I don't think CLI was available, or was it? But wait, hold on. Okay, but so what's the solution? You have to pay $20 or something? No, but yeah, so Copilot. But Copilot, I tried it, and it's a little confusing at this point, right? So it's not. Say again? But Copilot is free for students. But did you try it? Does it even work? Like, I mean, I tried and I was so disappointed that I just dropped it right away.
Yeah.
Oh, so if you choose the right model, then it works more or less. But then you have to pay for the model.
No, because the program is free.
GPT Pro.
Copilot.
Copilot Pro is free for students. Okay. Oh no, that's cool. So then you can like you can skip paying still, right? For now. Okay. So that's did you guys follow the discussion? So the idea is that suddenly last week university changed our access rights or whatever they are paying for ChatGPT, OpenAI APIs, right? And I wasn't sure what's going on, and I still don't know. I don't think anyone knows, honestly. So, but I think ChatGPT Pro is gone, and from what I understood, Codex is also gone, right? Only Codex.
So technically, this is one chat.
Okay, so but you say that if we still have access to Copilot, right? And it's still paid, and it's supposedly. Yeah, no, and I was kind of pushing for VS Code to begin with, just because it was the easiest. But I don't know, like maybe I'm wrong, so I don't have that much experience. Okay, so then let's still use it. I mean, again, it's very awkward at this point. Say don't use AI tools in this class because the assumption is that you already kind of know how to program a little bit at least. And second, if you don't know, you will still cheat anyway, right? So there is no way for me to enforce. I mean, I can go like and try to enforce something, but it's kind of not very nice. But those homeworks which we're going to be doing, some of them are kind of geared towards it. Like otherwise, you have to write a ton of like very carefully crafted C code, and it's a little tedious, right? So debugging it. So let's go with this. Okay, cool. So you said that homework is coming along. Yeah, it's not super hard, especially with the AI tools. It wasn't hard to even without them. So you can write the shell, but you have to very, very carefully like keep track of how to fork, which pipes to clone, which pipes to like, which file descriptors to close and stuff like that, right? AI probably helps just drafting this skeleton for you immediately, right? Okay, so any questions about anything else before we start? All good. Okay, so back to linking and loading, right? So we're going to spend a little bit of time on it. So we're going to talk about it today, and we're going to spend some time on Thursday as well. And the plan for us is to understand how the programs are linked together and, more importantly, relocated in memory. And also how they are loaded from memory into the address space, right? Because when we're going to look at the code of the exec in x86, or even when we're going to be looking at how x86 is booting, we have to understand how it works, right? But then we also will take a look at how position-independent code works, and that's mostly for the reasons of just being able to understand what's going on like standard Linux systems, right? And okay, so coming back to what we were discussing last time, we were looking at a like more or less generic diagram for how the programs are linked from multiple object files. And this is kind of like a high-level overview. What was more interesting was kind of this diagram, or even maybe this diagram, where we say, look, at a high level, what happens if you compiled multiple object files like A.O, B.O, C.O, what the linker will do when you link them together, it will start merging them into a single potential executable, or maybe a shared library file or something along those lines. And internally, what happens is that, roughly speaking, inside each of those object files, there will be three sections: the text of the code of the program itself, data section, and BSS section, which contains zero initialized variables, right? And what happens internally is that the linker will take those sections, like text section from all object files, A.O, B.O, C.O, and it will merge them together. And the same will happen for the data section and for BSS, but BSS is easy because it's just all zeros, so you just initialize something with zeros. But the question which we were like trying to discuss last time is what really needs to happen to the program, right? Because imagine you had imagine you had a text section and a data section, and the text section was accessing some variables in the data section, right? And now suddenly this text section, maybe it didn't change location in memory or anything, but was merged with some other text section, which is like now sitting next to it, right? And this data section was also like moved somewhere, and the data section from another program was moved here. And obviously this address of this variable A, imagine you have an instruction which still tries to access A, it cannot access this address because really it's no longer a data section, it's now code of the program. And so this reference has to be changed to a correct address, right? That's the high level overview of what we're gonna be looking at today, right? And also that's the act of linking, but sometimes you say, look, I really compiled and linked my program to run at address 0, but I want to move it in memory to some other address, right? And there will be different reasons for that, but let's just imagine we have one. And again, if you're using an absolute address here, and if you're moving everything in memory by some delta, obviously this address should also be changed by a delta, right? So that's high level overview, but let's take a look at what's going on inside, right? Let's take a look at a couple of examples, and we will first take a look at the example of relocation. So meaning that just moving program in memory. And again, just for the sake of example, let's imagine a very simple sequence of code. Specifically this assignment of A is assigned to B, right? Which gets compiled to something like two assembly instructions. I use AT&T assembly, so it goes like this. A is loaded. The address, we use address of A to load the content from memory into the EAX register, and then save this from the EAX register into the address of B, right? Make sense? And sure, imagine for a second that right now A is known to be at address 1234, and B is, let's say, imported, meaning that it's not known in this file. So specifically, user said something like extern int B in C code, right? So the compiler knows the type, it knows that it's an integer, but it says, okay, well, I don't know where, like B will come from another object file, right? Make sense? And so sure, like the compiler gets like generates those assembly instructions. So again, since it's from last year, I'm still using 32-bit assembly, but 64-bit will look very similar. So this move of A into EAX gets compiled to this instruction. Move of EAX into B gets compiled into this instruction, right? And again, if you like look more carefully, you say, look, this instruction has a single byte opcode, A1, that specific value actually, which encodes this move. Then we have a 4-byte address, 32-bit system, right? And our addresses for A is 1, 2, 3, 4, right? And just because there is this notion of endianness, right? So on our system, essentially, like there are two ways to encode these addresses: little endian and big endian, right? And so the memory grows this way, and our address is 0, 0, whatever it is, 1, 2, 3, 4, right? And we encode it actually as in the opposite direction. So like, or like, hold on, just so one way, like if you have an address A, B, C, D, so one way is to put it A, B, C, D, and the other way is put it in the reverse direction. And this is exactly what we're doing here. We have 0, 0, 0, 0, 1, 2, 3, 4. And that's why you see this instruction coded like that, right? Make sense? Okay, so we're in a little endian system. Sure. And since we said that B is exported, the compiler says, okay, I don't really know where B might be. So for now, let's just put 0 as an address, right? Okay, sure. And then imagine later on, like when everything gets linked together, so maybe like the specific code, these two instructions get merged with another object file. And at this point, you know the address of B, and you also, the data section where A was contained is actually moved by, like relocated in memory by, what is that, X 10,000, right? And B is found at this specific address. So the end result of this relocation should be that you have to patch those addresses. So specifically, addresses were used within the instructions themselves, right? So here, since you shifted the A variable by X 10,000, right? So you add this O1 here. And since now you know the address of B, you put it here, right? And so that's what happens when the code is relocated in memory, right? Every time you access a variable, every time you use an absolute address, you have to go and patch those addresses in your text section. Just the addresses are contained in the text section, right? Make sense? Like that's the gist of what needs to happen. And essentially, we need to preserve enough information in the object file to make sure that we know all the locations in the text section which need to be patched and how they need to be patched, right? So essentially, you have to record the fact that here you have to put the address of B, and here you have an address of A, but in case the data section gets moved, you have to patch this address, right? Question. Say this again. Like essentially, what would be the reason for relocating a binary? Most often, like again, most often what happens is that you really just linking and you're just merging multiple object files into one, right? And then those addresses, since everything was compiled essentially, let's to start at some default address, and we can pick 0 for now. Now only the first one can stay at 0, and these will be at some addresses A and B, right? So essentially you're relocating the two other object files, right? But also it may happen that when you create a process, when you essentially the operating system might decide to implement a specific policy, and for example, for security reason, it says, look, I'm not going to be running code at address 0 because any null pointer dereference will allow me, for example, overwrite code at address 0. So we will just shift everything and like load stuff at a specific address which we pick, right? And so you're just shifting something in memory. Another example of relocation is when you use shared libraries, and essentially you say, look, my library was linked to run at the specific address, but this address is not available. So essentially, when I be loading this library in memory, I will just shift it by some constant to make sure that I can fit it somewhere in library, in memory. In practice, this story gets a little bit more complicated, and bear with me until we reach position independent code. So in the past it was done this way, but today it's not done this way. So let's just, but in general, again, the idea which we all have to remember is the fact that essentially, if the code uses absolute addresses, and often when you load the code in memory, you will have to reflect the fact that you have to change those addresses. Okay? So here is this is just very, very naive example, right? So here is a more involved example, more realistic, where you say, look, I have two C files, m.c and a.c. And what happens here is that I have a couple of functions here. I have an extern function a in m.c, right? And again, you say, look, you define it like that. Compiler knows the return type. It does know the arguments. It knows the function signature, so it can generate this call side. So it can know, it will know that there will be one argument. It has to be on x86 system, on 32-bit system, it will be pushed on a stack. On a 64-bit machine, it will be passed in register. So it can generate this call side, but implementation of this function A is in another file. So it's implemented here, right? And so specifically what happens here, the main function has a string in a global data section, hello world. It passes this string into the A function, which is implemented in another file, takes a pointer to the string as an argument, and uses the write system call, passing file descriptor number 1 as an argument, and then passing the buffer S and the length of this buffer into the system call, right? Just a very simple example. If we look at it, and you can compile it yourself, and we'll talk more about what all this means and how this information can be obtained, but you can use optdump or readelf, and we'll get to them in a second. But at a high level, what compiler did here is said, okay, look, I generated two sections. So a text section, which contains the code, and a data section, which contains the data. They happen to be so short that both of them are 16 bytes long. This is 16, right? Essentially, right now, what happens is the code section is linked to be loaded at address 0. The data section is right above the, no alignment, nothing, right above it at address 16 because it's 16 bytes, right? And sure, so you see that if you look at the disassembly of the code, the main function, which, I mean, it doesn't have to start. If you have multiple functions, it's not guaranteed that main will be the very first function and in the code section, but it happens to be here because it's the only function. So it's right now at address 0. And again, our lovely 5.5 kind of an opcode for the push EBP, because we maintain the stack frame here, right? And its example again uses AT&T assembly and uses 32-bit code, right? Okay, if we look a little bit more, we see that, okay, sure, we're pushing this string. Since again, it's a 32-bit example, the calling convention is that argument is passed on a stack. So we're pushing the code itself here says, let me just click on the code. The code here, just one argument, which is passed inside A. So, and what we're doing here, we're pushing this argument on a stack. Since we know exactly that right now it is at address 16, this is where the data section is located right now. The compiler generates this 16 in a little endian way, right? Okay, that makes sense. However, so that's essentially what we did here. Let me stop here for a sec. Any questions about this file? What I meant to say, however, means that obviously we say, look, what should happen to this file if suddenly this text section is merged with some other file? Like, for example, we are currently compiling two files, a.m and c.m. And obviously, if they are linked together, A and the text sections of A and C will be merged together. And so something has to happen to those addresses. And if we ask, like, I wanted to ask you first, like, which addresses will need to be changed here? Like, again, here's the source code. We're looking right now at this one. Okay, sure. Like, I'll pick a person in the back. Correct. So this push instruction, which pushes this static variable hello world, the push instruction uses some error here, right? And we have to change it. Agree? So in our assembly file, it specifically sits right here, right? So this address will have to be changed. What else? Just go back to the source code. Anyone else? Any other?
You have to change the address of the.
Correct, right? Because you say, look, I don't even know the address of A right now, just because I said it's extern. So I know enough information to generate the call side. I know that it takes one argument, and it's like whatever, a pointer argument, and it returns void. So I don't have to like do anything with AX or anything like that, right? But you don't even know the address of A, right? And that's why essentially what we have here is that for the address of A, compiler actually just generates some dummy address, right? So right now for the address of the hello world string, it actually generated the address which points to the data section. But for the address of A, it doesn't even know this address. So it just puts some numbers here. And conventions vary. Like some compilers just put zeros here, and most likely we'll see zeros most of the time. But essentially, it just says, okay, I don't know where it is. And in this specific case, it puts this number. And if you carefully think about this number, and it's not always the case, not all compilers do this, it actually put -13 here. So because if you take a look at how it's encoded, so it's -13, and what it like essentially where it goes, it just calls, for now, it just calls the entry point of the program. I don't know, you can say that it's a safety mechanism. So essentially just jump, if you somehow just, it happens that you screwed up the linking and you're suddenly running this code, it might be a little bit easier to debug. Sometimes what happens is that it just loops around and it calls itself. It will not help you to survive for too long because each call will push something on a stack, so you will run out of stack and crash anyway. But maybe at least for a human, it will be a little bit easier to catch the bug that it's a linking bug. In the case, okay, well, do I ever see a linking bug in my life? Well, when you will be working on x86 homeworks, you might, right? So, but essentially, like you can very well put like any number here, any number which will help you to debug the program, right? You know, -1, all Fs. Probably -1 is not used because no, it can be used as well. So essentially, I was thinking that this address has a meaning on a real system, but it's not accessible to the user level code. So inside the kernel, it will be leading to a bias accessible region. So maybe that's not the best idea, but you got the point. So essentially, some addresses here, right? So these two addresses will need to be essentially changed, right? And if you invoke this tool with flags, like essentially asking the tool to say, please annotate give me all the addresses which will need to be changed. The tool itself provides you this helpful information. It says, look, starting at byte 4, because byte 0 is this one, 1 and 2 are these, this is byte 3, and this is specifically byte 4 in the program. Change this, and it's a relocation looking into, it's a 32-bit address looking into the data section. We'll talk about those relocation types, right? Here it says, okay, look at byte number 9, it's a relative address, and the reason for that is that the compilers actually, like, there are multiple reasons for that, but the idea is that you can generate call instruction in such a manner that you use relative addresses, right? You can use absolute addresses, you can use different registers and like stuff like that, right? But call instruction allows you to say, look, this is relative, this is call is relative to the current position. So essentially, if you at some address A and you put some address here, typically it means that you add the size of the call instruction itself. So if you have the next instruction, and this is delta, which can go either negative or positive, and you're just jumping and calling stuff from this delta, right? So essentially, if you're calling B here, so you will add like this delta is, I don't know, let's say 55, then you will put this 55 here, right? So, and then, okay, the reason for that is that actually it might be later easier to relocate instructions in memory, because if you have relative addresses, you don't really have to change them, because as long as you have a guarantee that everything moves together, you don't have to do anything with those, right? So compilers use those relative addresses, right? But essentially the point here is that when I will be asking later, like what needs to be relocated, you can always, I mean, first of all, think about whether your code uses any absolute addresses, right? Or like whether it has some missing addresses, because it tries to replace this with the relative address. The moment the relative address is known, you don't have to do with it, because if you move it in memory left or right, then the distance between the target and the call site don't change, right? Doesn't change. But essentially here, like if you do this thought experiment, you say, look, I know that my program will use two addresses. Like again, if we look here, it will use the address of the string, and it will use the address of the a function. And the reason compiler doesn't know where a is just because it's external to this module, right? So then those two will need to be patched. And if you say, look, but I'm not sure, you can invoke this tool and take a look at those annotations. The tools will provide you this information saying, okay, those two will need to be patched. Any questions about this? All good? Okay, so far so good. So let's take a look at the second file, right? So again, so now we're looking at this one. This one invokes a system call. Compiler again generates two sections, one text section, one data section. Data section sits at 0. Data section. Okay, text section sits at address 0, virtual memory address 0. Text section sits at 0. Data section sits at 1C. Why is that? Because the text section itself is 1C in size. Data section is 0. It so happened that we don't have any global variables, right? So nothing needs to be like, no memory needs to be allocated for this section, right? And again, let's do the same thought exercise. We take a look at this specific function, and since we all followed, let's quickly do a poll and try to understand what really needs to be relocated in this file. So hopefully you can see it. So it goes line by line. So it says, okay, line 3, 4, 5. There are some arguments. Again, don't forget that what you need to like remember how we go about it. So we say, look, when my code is using an address, then this address needs to be patched by the linker, right? So essentially, think in terms of like, terms of, oh, Jesus, like here I linked it to you. I did? Yeah, unfair. Okay, look at this one. Which parts of this code use addresses? S is here, but what is special about S? It's a pointer to an address. Okay, anyone? Okay, let's discuss about it a little. It is because, I mean, the fact that we have a poll and someone like fails it or someone doesn't matter that much. What matters is discussion. Okay, what is special about S?
The address
Okay, where like yeah, so pointer is in the stack. So what does it mean? It's relative to the stack. Do you need to relocate anything if you're like if your variables are allocated on the stack? Because the way you use the addresses will be something like push, oh, I'm sorry, not push, let's say move, something like EBP, let's say plus something, right? So EBP doesn't, it's not an absolute address, right? EBP will have a pointer to the stack and you say relative to the EBP, I'll find the location of my variable, right? So the code itself, like literally, if you have an instruction which gets generated for accessing S, right? It doesn't need to be changed, right?
So the string length, is that system call or is it?
Libc call, right? That's a great question. So correct. Wait, hold on. That's a very smart observation. So first of all, like we saw this example, we saw that when we use a function A, we don't know where it is, right? So we just have we declare it as extern. When we use those functions like write and stringlen, we include them through include files, but really like we don't include implementations of those functions. We just essentially those includes are kind of similar to this extern declaration. We just say, look, here's your function signature, but implementation is opaque, right? And it will be provided at linking time. So it's essentially this, like, in fact, it's almost like you can either say include something, or you can say extern write, whatever it is, like int, whatever char pointer, maybe another int as a size, right? So it's also just an extra declaration factor, right? So again, yeah. Oh, it only allows you to pick one. Jesus Christ! And how do I fix this? Response settings as many times as they like, right? Okay, now you get okay, good. Everyone reevaluate the options, right? Yeah, we're converging to a better answer. Yeah. Sorry. But I wanted to, again, it's not as important to make sure that, like we penalize someone for not following the discussion, but it's more important to think about what really is going on here. So before we even close the poll, so I would like to, again, take a look at the code of it, right? So essentially what happens here, right? So this is okay, let's just discuss it. So step by step, I'm not going to close the poll. I'll make sure that I'll be explicit and you will be able to finalize your answers. But let's take a look at what needs to be relocated here. So essentially at a high level, the answer is that you need to relocate those to the addresses of write and stringlen, right? The reason why it works this way is the following, right? So the body of A itself, which is like, again, compiled right now to be at address 0, it maintains the stack frame. So it's like pushes EBP, initializes EBP with the current value of ESP. When it generates the code, the call site for stringlen, and again, it's a 32-bit example. So the first argument is pushed on a stack. Right now, this first argument is contained inside the EBX register. So it's a pointer to the string. Where we got it from is that we use the address relative to EBP, right? So in Intel assembly, it would be EBP plus 8. And we save this. So essentially, this variable itself, the address of the string is on the stack, which is at the position EBP plus 8. We save this address into the EBX. and then push EBX on the stack to pass it into the string, right? So which means that this address S, the use of this S doesn't need to be relocated. It came in relative to the stack. It's a local variable. I mean, it's an argument, really. It's not a local variable, right? And we use it and we know that this argument is sitting on a stack. In a 64-bit assembly, it will be in one of the registers. Which one is the first? RDI. And so it will be sitting inside RDI, and really like you wouldn't be doing any of this, and you probably would just leave it inside RDI and just like call a function string len, right? Make sense? Okay, so we call, but in order to call string len, we need to know its address, and we don't have it, right? So because it's inside the include, it's effectively an extern, and so we say, look, the compiler says, like, okay, sure, you will have to come back later and patch this address. The same for write, right? So, and write itself is not immediately a system call. It's a wrapper around the system call provided by libc. It takes 3 arguments. So the compiler pushes those arguments on a stack. So remember that when we call the string len, it returned the number inside the EAX register. So the string of the length of the string is already there. So we're just pushing it on a stack to make sure that it's passed into the invocation of write. We're pushing the address of the string EBX, which we saved here, on the stack as well. And we're pushing number 1, saying that please use file descriptor 1 as an argument on the stack, right? Again, in 64-bit assembly, it would be inside RDI, RSI, and where's the third address? Third argument, I already forgot, but in a third register, right? And then we call write. And again, the compiler says, okay, I don't know anything about write, so I will just be generating this dummy address, negative to jump back to 0. In fact, it just shows you that I'm calling address 0, but if you invoke it with specific like relocation information flag, you say, look, it's actually trying to find the symbol write. This one is trying to find the symbol string len, right? So these two have to be relocated. Make sense? Everything else is just like relative to the stack. And so everything else is nice, right? And we say, but what about? Yeah, only the second. And the question itself says, okay, we are asking relative to those string numbers here. So essentially, the correct answer is just in string 5, relocate the use of write and the use of string len. No, like the rules of thumb is that you have to relocate all absolute addresses or the addresses which are not known to you. And so absolute addresses are addresses in the data section. They can be, or addresses of functions which will become relative addresses relative to the position in the call, relative in the text section. But at this point, since it's still extern, it's still not known, right? But essentially, the way to answer those questions is to make sure that you understand that this is just a constant. 1 is a constant, so it's will not be an address, right? But this S here is an argument inside this function, so it's again relative to the stack. The string here is declared as static, so this goes into the global section. And if I'm using it, so this will require an absolute address in the data section. If I'm using A here, and I don't know where A is, if A were to like defined in the same file, if you would have something like int A already here, then this address, it's a little tricky, but you can argue that this does not require relocation because the compiler can generate a relative address to call this int A. It's a little tricky because I think it actually might not do that in all the cases, but let's go through those maybe last in the next lecture. Otherwise, it gets too complicated, right? Make sense? Any questions about this? So I mean, and I didn't really strictly gave you all the rules, which probably Okay, we have also deactivating the poll right now. Everyone answered, right, in the room. Right. Okay. And thanks for telling me that my poll was misconfigured. So okay, but at least we got the gist of the problem, right? And essentially, the way to be really like careful and specific about what's going on here, you can always invoke those tools, but ideally you should have a mental model, and the tools will tell you, okay, here I'm looking for the address of string len. Here I'm looking for the address of write, and those are the two things were in this file which will require patching, right? We're like doing some linking or relocation here. So specifically, like in this specific example, we don't even do relocation, we're just doing linking, right? Because we're merging the text sections and we're saying that those two symbols are external, so we don't really know where they are.
Within a function, itself is actually calling a string inside of it. So why?
Okay, that's a good question. So who can tell me? So there is this one line, right? It's a write function which takes 3 arguments, and it's written as string len is passed as one of the result of the string len is passed as an argument to write. So the question was, why is that really string len in the code appears before invocation of write, right? So who can tell me? It's not a hard question.
Write needs to be out as an argument, so string first.
Correct. So do you agree with this? Right. So because like the fact that we wrote the code like this doesn't mean that we're doing this way. So what we're doing is that, let's say arg3 here is string len of s, arg2 is s, and arg1 is 1, and then you're just invoking call of like arg. Sorry, what I wanted to say, you're invoking write with arg1, arg2, and arg3, right? And so logically, this code which is required here needs to be computed before, right? You can compute them out of order, and I don't really know, like probably compilers do not limit you, and you can say, look, I will first compute second argument and the third argument, and maybe they're already computed in my code somehow because you're just passing them. But really, I need to invoke string len first, get the value of third argument, so I can pass it here. And the dependency goes like this, right? Makes sense? Right? And it's again, like it makes sense to take a look at what compilers generate underneath, and that's what we're doing here. So like it's 2 invocation, one of a string len, and second of write, but really everything else is relatively simple, right? Any other questions about this? All good? Okay, so that's a good question. So remember, I was kind of complaining that when I was younger, like there was a chance of running into different ABIs even on the same system. Right now, the chances are lower, right? So typically, you will have one ABI, but you can have like, imagine you're calling a function A, and A comes from a different object file. And really, you don't know how this A is compiled, right? So this object file is compiled. You don't know whether A maintains the stack frame. It composes nicely because the idea is that no matter what you do with this register, EBP or RBP, right, you have to restore it, right? So even if you don't like maintain the stack frame internally, because maybe like it was compiled somewhere else, like and shipped to you as a binary, right? You'll be fine invoking this function. Like it will not break the ABI, right? Just because this is the call is saved register. So A has to save EBP anyway, right? Whether it's using it for a stack frame or not, it has to be saved and restored, right? If, however, you're mixing ABIs, then it becomes a little bit harder. So like, and sometimes you say, look, I'm calling into, and maybe this library came from Windows for whatever reason, and you still know you can invoke it and say, look, I'm so clever that I can invoke this library, which was compiled for Windows. maybe it's some numerical library, doesn't touch any system call, but just computes some matrix multiplication. It will work, but you might have to create a shim, which essentially a wrapper around this ABI saying, I will save and restore everything according to my ABI in order so nothing gets broken, right? Right. But essentially, I forgot exactly what you asked, but that's my answer. What was the question? I forget.
All that we call functions of stack files, whether we need to
Right. So strictly speaking, no. Right. It can be mix and match, and you can even switch between ABIs, but then you have to be extra careful about how you like to make sure that you preserve your own ABI. So to essentially, when you return here, all the registers which this code expect to be restored are restored. Any other questions? Okay, so we got it. So we kind of understood. Okay, we have a rough idea of what needs to happen within the code when we merge them. So we now understand this picture and this picture much better. We say, look, we got it. So we have text sections, we have data sections. We're just merging them, and essentially the compilers will the linker, which is responsible for merging, will do it correctly. Let's take a look at what happens internally. So not surprising, again, like if we link those two together, we'll again end up with three sections: text, data, and BSS. They now moved in memory. So this is one example where you just had to relocate all the sections in memory. They no longer start at 0. They start at this address 1020. Data section starts at 2000. BSS start at 3000, right? They have different sizes. So this one is this is a specific size for each of them. Now, there is some startup code which runs before main. We can discuss it later, but at some point you say, look, I will call main. Again, I'm using a relative address. So it's just, it's an offset from if you start at 992 here at 1092, then, and this instruction is 5 bytes. So 1097 plus D will land you on this address. Like we can do the math if we want, but essentially it's a relative call address. We're calling main. Inside main, we now have the address of the hello world string. It happens to be in the data section. Data section started at 2000. So it's within the data section and the address 2024. And this is why it's written like that. So we're pushing it as an argument to an A function. We already know the address of A. And since we merged everything together, we can generate a relative call here. So it's +3, essentially calling this address. Inside, like this is explanation for the relative addresses, like again, the slide. Inside A, we're calling two functions, stringlen first, and again, everything is already merged into one data section. So we essentially, on purpose, we generate the binary, which is self-contained. We don't assume that this will be linked anymore. So it just essentially can be loaded in memory and executed. So essentially, relative call to stringlen, relative call to write, right? And so that probably, essentially, the final executable looks like that. So any questions about this? So essentially, we just merged everything together, patched the addresses, right? And we said, okay, we have to patch the address of the string itself. After that, it's passed in the register on a stack, right? And we patched the invocations of the main function itself, the invocation of A, invocations of string, invocation of write. Make sense? Okay, cool. Let's take a look. I keep saying that we somehow take C files.c and generate object files, right? And we somehow, later on, we can merge multiple object files, and linker does it for us. But essentially, in order to perform this merge, we obviously need bits of information, right? So what kind of bits of information you think we need to successfully perform those merge steps, which I kind of was talking informally about? the size of each file, or one would even say the size of each section, right? So you say, look, I have a text section, I have a data section. I optionally might have like a, let's say, virtual BSS section. So you need to know the sizes of those, right? What else? In order to merge them, like from two files, for example. Size is not just enough, right? What else do we need to do? You need to know, yeah, you need to know some relocation information. So you need a table which keeps track of where in the program, in your text section, you have to apply your relocations and how, right? Some of those are in a shape of, I don't even know where the address is. I just need the symbol A, or I need the symbol streamland. Others are like, I'm right now have an address which points into my own data section, but I'm pretty sure that if the data section is moved in memory, I have to patch this address, right? So we know two kinds. One is not known, and the second is have to be updated as we move stuff in memory, right? So you need a table for relocation. I agree with this. What else? No, like you mentioned sizes, but you can't really do anything without knowing where. I mean, you can, roughly speaking, if you know that if this starts, if you have a tiny header here, which contains those information like sizes of each section, then you know that if right after the header, the text section is, and after that, you know the size of the text section, if you say, look, right after that, there will be a data section, sure, then size is enough. But typically, to be a little bit more flexible, you also will need positions of those sections within a file, right? Just to make sure that we can find them in a file and merge them, right? Sizes is not enough. But okay, that's pretty much it. So, but let's take a look at a couple of things, right? So you named all of it. So typically you have a header which contains like metadata information, like sizes and positions of other sections. You need these the code and data sections themselves. You need a table with relocation information, right? And optionally, you will have some debug information as well, right? Because you say, look, I wanna, like, for example, as a step through the program, I wanna show the source lines on the screen, then you have to include them into these files as well, right? And the very first, like the reason we talk about it, it's for historical reasons. You probably, even now, you will see this name A-out. They just quickly cover what this A-out is. So A-out was one of those first container files for the object file. So essentially the layout of the file was exactly like it's shown here. So there was a tiny header here. Then there was a fixed order of those sections, like a text section right after, data section right after that, then other sections, right? And essentially, if you wanted to load an A-out, you really just had this definition of a C structure, which says, okay, it's byte compatible with the A-out header. So the very first 4 bytes were a magic number to check that whatever you're loading is really in A-out file. Then you have the size of the text section, size of the data section, size of the BSS section, size of the symbol table, which contained like relocation information, entry point where to start executing the files, and essentially 2 tables for text and data relocation information. And essentially, okay, sure, it was very, very easy. You still, like, occasionally, you see this, like when you invoke GCC compiler, it produces A-out. It's actually not A-out anymore. What GCC will produce is ELF container, but for historic reasons, the name of this file is still A-out. Right, and then you got the point. So if you have this information, you can like easily like take a look at A-out header. If you say, I want to load this file in memory and start running it, and it'll say, like, if it's self-contained, like this example, which we have here, essentially everything is linked to run at essentially virtual address, at this virtual address. Then you simply load this thing in memory. You say, look, text section goes at this address, data section goes at the section at the address of the data section. BSS is allocated on top. Then you allocate the stack, and the heap is allocated dynamically. At this point, like you have an entry point in the program. Let's say it's like something main. Maybe it's main, maybe something else is running before main, but essentially you can set instruction pointer to point to this location. And at this point, you can start running. So roughly speaking, this is what will happen inside the exec system call, right? So if you're loading an AOut file, make sense? And we will take a look at how exec works, but okay, sure, just preliminary setup. Let's just understand at a high level how it works. Okay, cool. AOut turned out to be not super flexible because in reality, we have multiple use cases, and majority of those, like at least 3 major use case is then when you have an executable file, and this can actually be either statically linked, meaning that it already contains all the dependencies, can kind of be loaded in memory and immediately executed, or can be dynamically linked. And it might depend on dynamic libraries, right, which have to be loaded into the address space of the program. But the other 2 strong cases are static libraries, which you link against exec files, and dynamic libraries. And so in order to support all of these use cases, and I will explain them one by one, people said, okay, AOut is not flexible enough. And they came up with this more generic format, or rather completely generic, which can represent all these cases, which is called executable and linkable format, or ELF, right? And this is exactly when you look at your Linux system today, it will be using those ELF format, right? Okay, so ELF was designed specifically to support individual object files, static libraries on Linux, on Unix system extension .a. A stands for archive, shared libraries, extension SO, and executable files, which are linked and ready to be loaded, right? Conceptually, like it represents the same information as AOut, but it maintained in a more complicated and a more generic way. If you look inside the ELF file, you'll again will have the ELF header at the very top, right? ELF header will contain, as usual, magic number to make sure that we really like talk about the ELF file itself. Will contain the entry point for the program where the program has to start running. And most important distinction that it contains pointers to two tables. One is called a program header table, typically sits right after the ELF header, but actually there is no strict requirement. It can be anywhere within the file. So since these pointers, like essentially if I have a pointer from the ELF header to the program header table, it's an offset within a file. So it can be anywhere within the file. And at a high level, this program header table is very similar to AOut. It's used to just load sections in memory and start running them. The second table is a section. This one is a program header table. This one is a section header table. It typically sits at the very end of the ELF file, but again, not strictly required, because you always have a pointer which points to it, right? And this table contains enough information about relinking or relocating the file. Essentially, if you want to merge multiple sections together, all the information will be here. If you want to just simply load the file in memory, information will be in the program header table. This section is used by the loader, and this section is used by the linker, right? Okay, let's, again, a little bit complicated, but like essentially those two tables provide kind of like two different views on the ELF file. So let me erase everything on this screen. But conceptually, you see I have two colors here, green and blue. And the green color, which all the pointers from the program header table just describe how stuff has to be loaded in memory. So it essentially says something like, this has to be loaded as executable. This part of the file has to be loaded as writable. This has to be loaded as read-only, right? And it's all like kind of like in the green view. This blue view can conceptually say, look, within this executable, there will be two sections, one init, one text. They're separate. They're just like merged together and ready to be loaded at the same, like next to each other, but they're semantically different. And inside this writable section, there will be a data section. There will be a read-only section here, and all of it is accessible through those essentially blue pointers from the section header table. So kind of two views of the same file. One view is used for loading, the green one. The blue one is used for linking and relocating, right? But just to make it concrete, okay, any questions about this one for now? I get it that it's like, it's still like hand wavy and not clear what's going on, but. GOT, global offset table. So we'll cover it as well. So GOT is used for generating position independent code. And I will explain what it is. We didn't talk about it. Yeah. So, and there will be like more funky sections, and some of them I will not know the answer, but GOT is important. That's why I put it there. We'll talk about it. It's kind of important. Any other questions? No. And in fact, it's not, I mean, it's important to a degree, but it's not fixed. So remember when and we'll see it in X6, on this kind of goofy looking diagram, which I picked from a book, and it's a famous linking and loading book. There is this entry, which is the linker control files. So linkers often have a language which you can program and say, look, I'm so smart that I want a specific layout of my program, you know, text section next to it, init section, but maybe you want init section to be somewhere else. And you can actually like kind of program, and X6 does it, and we'll take a look at how it's done. Essentially says those linker files essentially tell you where the sections go. And that's why the linker files can say, look, I need a specific order of those sections. Data, after data, there will be read-only data or vice versa. And it depends on like you as an operating system designer, you might make different choices. We'll see we'll take a look at the choices which X6 is doing, but essentially what it like translates to in this picture is that those sections can be kind of in a different order depending on how you specify them. And by default, when you compile a program on Linux, whatever the linker has from the libc or from somewhere, it picks up this specific linker script which it uses on Linux, and it's a hairy, complicated document, but essentially it encodes like default entry point for the program where it has to be default position of the text section and the address space of the program. On a 32-bit system, it's 1. On 64-bit system, it's different. Layout of those sections, essentially like one after another. So you will, in practice, you will always, you almost always will see the same layout, but it's really encoded by the linker file, and you can change it if you like. And ELF just supports enough information to like be fully flexible, support any layout. Any other questions? Okay, good. So, okay, let's take a look at a couple of examples. So just again, I'm compiling here on a 32-bit machines. I say, do not omit frame pointer. It's not very important. Generate a static executable, so no dynamic linking, nothing. Do not use position independent code. Forget about built-in libraries. And I'm compiling an example which you can access from the source code of on the website as well. So it's hello elf, doesn't matter. Like I'm saying, I'm using a GCC compiler, but passing -c flag saying that just compile but do not link. And later on, I'm manually invoking the linker saying, oh, please use the main function or main symbol as an entry point. And please make sure that everything is relocated to be ready to run at address 0. And the two files which I'm using one file, hello/elf, hello-elf.o, and producing a out, it's just random name. And then I'm like reading using the readelf tool to read the a out file. Readelf is a tool which allows you to read the elf format. And what it dumps here, it says, okay, I see an elf header. The magic number is such and such. So it matches the elf file. So it's specifically 32-bit elf executable. And you say, look, sure, like since we said, okay, make sure that everything is linked to run at address 0, then the entry point of the program, it happens to be 0. It doesn't always end up to being 0 because just maybe some other function is in the text section is before main. So this can be close to 0, but at this specific example, it's 0, right? And it has all this other information. It says, okay, within the file, the program header start at position 52, and a section headers start at the end at position 2980, right? Make sense? And some other information to figure out other sections, right? And if you look a little bit deeper, so essentially, again, let's take a look at this table first, program header table, because the reason like I ask you to pay attention, because in your homework number 2, you will implement a simple ELF loader. So essentially, you will have to open an ELF file, access those header table. So essentially, you follow this pointer from the header into this program header table. You understand that, okay, what's inside? And let's take a look at what's inside. So if you are in your homework to load something in memory, it's as easy as this. So essentially, you say you open this header table, you take a look at what's inside. So each entry in this header table is represented with the C structure. So now I'm using 64-bit system just to make sure that matches your homework. You say, look, this is the virtual address of this section. This is the offset within the file. This is how many bytes are in a file, because sometimes you don't store everything. This is the size essentially in the file, and this is size in memory. We'll take a look, but it's essentially when you have a BSS, you might extend a little bit and say, look, not everything is in the file, so I will add a little bit of zeros to the end. Flags, read, write, or executable, and alignment specification. And essentially what you see here is something like, sure, like it says, okay, you have the following entries in the program header table. You have 2 specifically. And you have to load everything what is marked with a flag load. And it says, okay, within the file, it sits at the offset 74. You have to load it at address 0. Again, not surprising, because we essentially said, okay, make sure that we compile and relocate and link this file A out to be ready to run at 0. In your homework, it will be a different address. Then, like this is an offset within a file. As I say, the BSS section is, so the size in memory is slightly larger. So it's 6C versus 6.8. So essentially what you do is that you read 6.8 bytes. When you load it in memory and you start at address 0, you read 6.8 bytes from disk, but then add a little bit of bytes to match this size and just put zeros here, right? This is yours effectively. This is encoding for a BSS, right? And then you say, look, what kind of flags I have here? So it's a little naive here, but all the flags are set. So it's read, write, and execute. So essentially, in order to execute this, start running this code, you have to make sure that the operating system configures the page tables with executable flags, right? Make sense? And so, and the second section here is a stack. So essentially, there is a convention. You don't have to do much with it, right? Because like typically the operating system just follows this. This entry allows the compiler to request a specific stack flags and alignment. So here it says that the stack is read write, so it's not executable. Some JIT compilers might require executable stack, or some self-modifying code sometimes does it, right? So sometimes you can see executable flag here, but a common security kind of discipline is to make sure that the stack is not executable, and alignment is 16 bytes here. So essentially, remember we saw that stack is aligned at 16 bytes, and this is essentially how it's represented in those sections. So essentially, what you do, like in order to load the ELF file, you read the header, figure out within the header the position of the program header table, and then like loop through all these sections. You found the ones which are load, you load them at this specific virtual address, and you make sure that you are reading those bytes from a file, adding a little bit at the end, not the whole amount, but just the difference between these two, right? and essentially mapping with those flags. Just ideally, don't forget the alignment as well. So it's a four byte aligned, right? So, but relatively easy. So loading of ELF, and you will see it in x86, it's not a big deal. So I just essentially just loop through those sections. And this is what we will have to do as part of your homework number 2. Any questions? Stop here for a second. All good? Okay. So, and okay, let's keep going with our scenario. So we mentioned, okay, so loading, if everything is ready to run, and like kind of in this example, I cheated a little bit, but I said, okay, like I say, no built-in, so no standard libraries, nothing. I just say, okay, like it will run, and I'm responsible for whatever I'm doing, right? And I say like link it at address 0. So this thing is an executable, it's ready to be loaded. Maybe it even runs on bare metal, like an operating system kernel. So for example, like if you somehow pass it to the bootloader, that thing will like will initialize the system, and this is essentially what will happen with the x86 kernel. But on a typical system, we have a couple of other scenarios which we want to support. And let's first take a look at something what is called static library, right? Who can tell me what these static libraries are? They have extension .a on Unix systems. What's inside a static library?
Oh, it's already.
Yeah.
You could look it in your.
Correct. So specifically, you have main, as we saw, .c. It uses something like a write system call, like one, whatever we pass here, s, string len of s, right? And you say, look, but I don't want to implement like my own binding to invoke a syscall through an interrupt or something like that. And I'm also lazy, and I don't want to build my own version of stringland because I trust libc developers to make sure that they like super optimize stringland function to run specifically super fast on my current hardware. So you say, I will use an include, like, or 1 or 2, right? And essentially what it include says, it's kind of like providing you extern style declarations. But the idea is that the compiler will use those declarations to generate the call sites for this too. But these implementations of these functions like write and stringland might come from some other libraries. And they can be like provided as static libraries. And essentially what you do is just you simply linked against them, right? And we saw the linking step. So it just merges everything together into one binary and it's ready to run, right? That's static libraries. Essentially, this is the story. So someone compiles those files. They come as ELFs with extension .a, but essentially it's an ELF file. And the static library is very, very simple. So it uses this archive format. So there is an AR tool, which you probably don't even remember. Like you probably never heard of it, but okay, 10 years ago when I started teaching this class, people still occasionally use this tool in practice, right? So I used it maybe once or twice, but essentially what's internally is like literally this. You take some files like printf.c, you compile it with GCC and you say like, do not link, just simply compile. So it produces an object file. And this archive tool just bundles this all object files together into one libc.a file. So it's just kind of like, it's really just an archiver. Nothing happens, no linking, nothing. Just, it's a collection of files, right? And it sits in your, like, you can either have like all these object files sitting separately in a file system, or they can be bundled into one libc.a library, right? And literally, like, you can invoke the tool by hand. You can say AR, some flags, generate me some library.a, and those are the object files which go inside. And sure, later on, you can pass this to a GCC compiler. GCC compiler, if you don't do this -c flag, will try to link everything. And it says, okay, for all like symbols which I don't find inside main.c, I will be looking into this static library. So hopefully I will find them. You can alternatively use this small l flag, and instead of like strip kind of down those parts of the name, just pass it like this. But effectively, it's it is equivalent to this. It's just like you're saying, compile this main.c file and link, and use those object files which you grab from this class library to resolve the symbols, right? So it's a very simple idea. Nothing is really going on here. Very simple, just an archival tool, right? So like just as an optimization, just because you have to locate where the symbols are within those libraries, sometimes, not always, but they can add, this archival library can have an index, essentially just like a map where each symbol is, right? But not much is going on. So what does this static library idea gives you as a, why do we need it to begin with? I mean, we discussed it, but I just wanted to make sure that we understand it one more time. What's the purpose of using static libraries? You lost me a little. Like, what do you mean, load one file? In the end, you know, like the end result of all of it, of this command, the output will be an executable file, which you can pass as an argument to the exec, and exec can load it into memory, set the instruction pointer, EAP or RAP, and start running from here. Of course, it will put a stack as well, right? But it's kind of ready to run. The high level idea is executable is ready to run. No linking, no relocation. I mean, in most cases, right? And so, like literally, we just said, okay, we use the static library to resolve all unresolved dependencies, like invocations, stops for the system calls like write, helping functions like stringlen, helping functions like printf, right? But in the end, all of it is kind of bundled together. In fact, like I'm not an expert on this, but when you merge files, it does not try to cut out the source with the file, the executable, the bits of the text section which are not used. You just literally merge everything together. So if you so happen that you say, look, I have bits of functions from all these files, all of them will be merged together, and it will be like rather large executable, but it will be produced and it's ready to run, right? Makes sense? So then what's the purpose of it, like of this technique?
So having a static library allows you to make your program entirely self-contained. So it's not going to have to come with like external dependencies or anything. You just have a program, you can run it. That's it.
I agree. So in the end, you can essentially say, look, this thing will run no matter what, because it has only dependency on the operating system, on the system call API, but you know, everything else is resolved at linking step, right? But what I was going after is that it's kind of a modularity mechanism, right? So it allows you to say, look, like how many people in this class ever looked inside libc? So maybe like 1 or 2 or 3, right? So not many. I looked a couple of times. I was horrified. libc is not a pretty thing to look at, right? But we all compile and link against libc. So it's like kind of like everything is modular and like put inside, and we don't bother. Maybe it was compiled in some funky way, like some fancy compilers, tool chains, configuration files, everything got compiled, packaged into the libc.a, and then I happily can just invoke this main.c minus L libc or like minus LC, right? And everything just works for me. So it's kind of like it puts a boundary between what I care about and what I don't care about. And someone cares about libc and a ton of different object files which were compiled differently, and I just link against them, right? So essentially those files are abstracted away, right? But they don't give much benefit. So I still, every time I link against them, a rather large executable file is generated. So I'm not saving a lot of space on disk, right? And I should really, every time I generate a main function, it probably will be like close to hundreds of kilobytes just because I included all of it, right? And so essentially this was not enough. And essentially what we're going to talk about next time is the idea of shared libraries. And essentially the idea how you can delay the linking step right until you start running the program in the process address space. Last question, and we are free to go. What goes?
Chromium. So.
Wait,
a
hold on.
lot of,
Like, well, sorry, like